So that's
We are not very strict in time, so you can go beyond 1 hour if you need.
Yeah, okay. So if I go beyond 1 hour, can you please tell?
All right. So hello everyone. So welcome to this edition of ICAT String Seminar. And today we have the pleasure of having Professor Pavel Kovtun from University of Victoria in Canada, and he's going to tell us about hydrodynamics beyond hydrodynamics. So over to you, Pavel.
Thank you, Joel, for the invitation. Thank you for the opportunity to present some of my recent results here. So I will be talking about hydrodynamics, which of course is an established field with a venerable history and many applications. But today I will not talk that much about applications. Rather, I would like to highlight some foundational questions that came to light in the last few years. So I want to give a very brief introduction to what hydrodynamics is. Basically, it is a set of equations that tell you how stuff flows. So stuff can be water, air, can be an atomic cloud or hot matter in an early universe, electron fluid in a solid, whatnot. And I remember myself as a student, and as a student, you open a book that has hydrodynamics or fluid mechanics in the title, and you often see derivations, approximations, and applications, and it's all going to be mixed together without much structure as a rule. And if as a student, you also learn about vector calculus and partial differential equations at the same time, it can be hard to see the big picture. But the big picture of hydrodynamics is in fact quite simple. So basically, it is all about conserved quantities. So hydrodynamics is a classical theory of things that cannot disappear, that is conserved. And when we teach about conservation laws to our students, we write it like this. So this is time derivative of some conserved density is minus the divergence of some flux. And this quantity A can be something that is conserved, energy, momentum, number of particles, whatnot. So another ingredient is what people call constitutive relations. And the way to understand them is like this. So you have this conservation equation, and it's basically one equation for both the density and the flux. And the biggest assumption of hydrodynamics is that you can take this flux and express it as some function or functional of that conserved density that sits in the left-hand side. And then what you have an equation that only involves this row, the conserved density, and that is something that you can potentially solve. So more generally, what people do, they take some quantities that I will call useful quantities, that I will call gamma. So this useful quantity can be temperature, velocity, whatnot, and express both the density and the flux as a functional of that useful quantity. So it may be necessary to do so for symmetry reasons, for example. And then this conservation equation gives you an equation for those useful quantities, which you can in principle solve. It will be a partial differential equation. Okay, so as a simple example, let's take the conserved quantity to be the energy, the useful quantity to be the temperature, and then you have to express the density, in this case the density of energy, as a function of my useful quantity, which will be energy density as a function of temperature. So this is something that is given by the equation of state. And the constitutive relation will have to express the flux, the energy current, as a function of my useful quantity, which is temperature. Of course, temperature is a scalar. To make a vector out of a scalar, you take the gradient. So you stick in some constant out in front, which is the heat conductivity. And then it's easy to see that for temperature fluctuations, you get the diffusion equation for delta T. Okay, so two derivatives in the right-hand side, one derivative in the left-hand side. Okay. So this is the summary of hydrodynamics. It has two ingredients: the conservation laws and the constitutive relations. So these derivatives, in principle, can include time derivatives. So I will be talking about that in a minute. Can be time derivatives and space derivatives. And you combine these two building blocks, and you get partial differential equations of hydrodynamics. And the procedure works the same, regardless of whether microscopic is quantum or classical, relativistic or not, superfluid, normal fluid, you have magnetic fields or not, and so on. So this is the summary of hydrodynamics. Now, with every theory we have in physics, we have to ask these questions. So every theory that we have in physics is only approximately correct, limited by its domain of applicability. And whenever you write down equations that attempt to describe physical phenomena, you have to answer these questions. Do the equations make sense? And two, what kind of physics is outside of the applicability regime of our equations? So what can we not describe? So my talk will tell two stories, one story for each of those questions, right? So this is the plan for the talk, 1 and 2. So the first story goes like this: do hydrodynamic equations even make sense? So you may think it's a weird question to ask because hydrodynamics has been around for a very, very long time. But it's not that simple. So let's say you're a student in subatomic physics or astrophysics, and you want to learn about relativistic Navier-Stokes equations. So you want to understand the quark-gluon plasma in nuclear collisions, or maybe you want to understand viscous effects in neutron star mergers. So as a student, you can try learning about the things from books. And when I was a student myself, books were still a thing. Libraries were still used. As a student, I came from the Russian school, or Soviet school rather, Soviet school of physics, and I was tortured through the course of theoretical physics by Landau-Lifshitz. And there is a volume of fluid mechanics by Landau-Lifshitz, and you open that book, and it has a section on relativistic fluid mechanics, and you see some hydrodynamic equations. Then I came to the US to do my graduate work, and I realized there are other books besides Landau-Lifshitz. So I had a copy of Gravitation and Cosmology by Weinberg. And also Weinberg has a section on relativistic fluid mechanical equations. So that is a formulation due to Eckart. And these equations that you will see as a student in Landau-Lifshitz and in Weinberg, these equations look very different. So as a student, I think it's fair to say that when you take a first look at them, you probably are going to be confused. So the equations look different, so what? As a student, you're taught to shut up and calculate, so let's shut up and calculate. And as a simple example, we can just work out linearized perturbations on top of thermal equilibrium state. Okay, so take a fluid, completely uniform, no external fields, no gravity, in flat space, look at infinitesimal perturbations of thermal equilibrium, and then you can work it out quite easily. And then you realize that both Landau-Lifshitz and Eckart's equations, they predict two things. One, they predict that thermal equilibrium does not exist, or rather that thermal equilibrium of a completely uniform fluid, no external forces, is going to be unstable to infinitesimal perturbations. And second thing, the equations predict that things propagate faster than light. Okay, so I put some reference to Hitchcock and Lindblom in the 80s, but these two facts, A and B, they were known way before those two papers. So what exactly is the problem? So if you look at infinitesimal perturbations of the equilibrium state, you look at these plane waves. So you solve the equations and you will find the dispersion relations. You would find frequency as a function of k. Okay. And when you look at these dispersion relations of the oscillation modes of a relativistic fluid, you will find that the modes come in two flavors. One type of mode is the gapless mode. So these are the modes such that when you take the momentum to zero, the frequency goes to zero. And so these modes exist because of conserved charges. So these modes correspond to normal hydrodynamics such as sound waves. So sound wave is an example of a mode like this. But the equations also predict that there is a different type of mode. These are gapped modes. So these are the modes for which the frequency stays finite as you take momentum to zero. And these are modes, moreover, they have positive imaginary part of frequency. So these are the modes, because of the positive imaginary part of frequency, they will give rise to instability in here. So these are unphysical modes. So we expect that fluid and equilibrium should not spontaneously explode. So these modes are unphysical. Now, if you think about these modes, you realize that these modes, I call them quote unquote fake modes, they're outside of the validity regime of the low energy hydro approximation. So these modes are, in the language of effective field theory, these are UV modes. But if you actually want to solve the hydro equations in practice, these unphysical modes, they're part of the equations, right? And they ruin predictability. So using the language of effective field theory, what happens in this classical description is that the cutoff scale physics messes up the infrared behavior. So there is no separation of scales here. So how exactly is the problem fixed? So the classic textbook hydrodynamics is not what you solve in practice. For example, if you want to study the quark-gluon plasma. The most popular fix to these problems is the so-called Israel-Stewart theory. And the way Israel-Stewart theory works is you take these equations of hydrodynamics, say from Landau, Lifshitz, or from Eckart, and you couple those equations to extra UV degrees of freedom. And this extra UV degrees of freedom, they're engineered in such a way that they kill the unphysical UV modes. So these extra degrees of freedom are the dynamical stresses and heat fluxes, in addition to the dynamical temperature, velocity, and the chemical potential. Okay, so I said that my useful quantities would be something that is normally inherited from thermodynamics. So something that you inherit from thermodynamics is temperature, velocity, and the chemical potential. But in the Israel-Stewart theory and its cousins, you also introduce other degrees of freedom besides those temperature, velocity, and the chemical potential. So this extra degrees of freedom of the Israel-Stewart theory that plays the role of a UV regulator. And so this is something that's different in relativistic fluid dynamics compared to non-relativistic Navier-Stokes, because in the non-relativistic Navier-Stokes, you don't need any extra degrees of freedom in order to have sensible equations that describe sensible physics. So other regulators, so outside Israel-Stewart. So can one find a regulator of hydrodynamics that actually does not involve introducing any extra UV degrees of freedom? So thinking as an effective field theorist, for example, in field theory, the Pauli-Villars regularization does introduce extra UV degrees of freedom, but say Dimreg does not. And so the claim is that in hydrodynamics, it is possible to do so. That is, there is a sensible relativistic hydrodynamics whose only variables are temperature, velocity, and the chemical potential, and no extra UV degrees of freedom. So the trick here is that you need to choose a suitable out of equilibrium definition of temperature, velocity, and the chemical potential. Okay, so how does this work in practice? What is this trick?
Sorry, I have a question.
Yep.
Sorry, so these unphysical modes with which tend to grow in time, they don't have anything to do with the presence of higher derivative terms, right? Or do they?
Right. So it depends. So these modes that exist in the say in the Landau theory or in Eckart's theory, these are the modes that are a consequence of the equations that do not have any high derivative terms, right? So the equations themselves, they are engineered that they only have up to one derivatives of the conserved densities. Okay, no two derivatives. And with that truncate at one derivative, you do have those unphysical modes.
I see. So this is not like the radiation reaction in classical electrodynamics, where again you have these blow-up solutions. It's different.
It's I would say it's different. Yes. Okay. Yes. So
okay.
Yeah. Right. So
hello.
Yep.
But though there's a certain sense in which they are similar, right? Because there are acausal solutions here also.
Yes. So the stability and causality are related, so they're similar in a sense that introducing certain kind of two derivative terms, if you wish, can take care of that in principle. But they're different in the sense that you formally speaking look at an equation that have been truncated at one derivative order. And of course, I'm going to talk about this on the next slide, how exactly you do the truncation that matters, right? And what exactly you call the one derivative hydrodynamics is ambiguous, yes.
But this is a similar statement also in the case of radiation reaction, right? I mean, if you kind of renormalize the mass, first of all, you have some divergences and you have to kind of take them into account properly. And yeah, and we know that if you make it to fermion, that something's happened, and if you include spin, something's happened regarding radiation reaction. So so in a certain sense, like there is a certain similarity. I don't know whether they are the same, but yeah, I'm not entirely convinced they are very different either. There might be some similarity.
Yes. So let me say the few next things that I was going to say, and then maybe it will be more clear in what sense they're similar and in what sense they are they different.
Yeah, thanks.
So how is this going to work in practice? So I'm going to argue for the following construction. So let's remember what we are taught to do as students in effective field theory. So the procedure to do effective field theory is this. So there are 4 steps. 1, we identify the low energy variables. 2, you write down all the terms that are allowed by the symmetry. 3, you do this up to a given dimension. Say this is 5 to the 4th theory, up to dimension 4, in 4 dimensions. And step 4, you look at the coefficients in your action and you constrain them so that physics is sensible. For example, the coefficient of this 5 to the 4 has to have a definite sign for the stability of the vacuum. Now, the proposal here, which is, I think, is extremely simple, is to let's do the same in hydro. Okay, so step 1, identify the low energy variables. And of course, this is always a non-trivial step. So I am proposing that the low energy variables that we choose to use here are temperature, velocity, and the chemical potential, because these are the variables that are inherited from thermodynamics, and they're conjugate to something that is conserved. And we know hydrodynamics is ultimately about things that are conserved. But there may potentially be other choices for the low energy variables. So step 2, write down all possible terms in the constitutive relations that are consistent with the symmetry. So for relativistic fluids, this would be Lorentz symmetry. And step 3, so we do this up to a given order, say first order in the derivative expansion. And step 4, constrain the coefficients so that the physics is sensible. That is, we demand stability of the equilibrium state rather than the stability of the vacuum state. Okay, so this is the proposal, which I think is not surprising. This is how I think many people are thinking or have been thinking about hydrodynamics. But let's work out, let's see what the consequences are going to be. So let's see how to implement this. So I want to write down the constitutive relation for the energy momentum tensor in the current. And let's pretend that there is some notion of the rest frame of the fluid, some notion of time, right? So with that notion of time, so the time component of the current, you identify as the charge density, and the spatial component of the current will be, well, the flux or the current. And similarly, for the energy momentum tensor, a 0,0 component is the energy density, the diagonal part is the pressure, the off-diagonal part is the stress, and the 0I component is the density of momentum or the current of energy. Now, if I take these statements and if I want to write them covariantly, so I pretend there is some notion of rest frame. So I pretend there exists a time-like vector u that is going to be a relevant degree of freedom for hydrodynamics, and so it's a time-like vector. So this is something that gives me a preferred rest frame, or rather the notion of time, the rest frame of the fluid. And the same statements in the first bullet point, I'm going to write them down like this. So this is going to be my current, and the charge density, rather than calling this J naught, I'm going to call this script N. The spatial part, I'm going to call this script J. So script N is the part of the current that is directed along my chosen vector u, and script J is the part of the current that is orthogonal to u. So this equation is basically just a definition of the letter script N, and it's a definition of the letter script J, right? So this equation has nothing to do with hydrodynamics, right? It's a definition of what I mean by script N and script J. And the same for the energy momentum tensor. So there's a similar decomposition in terms of some time-like vector u. So this E you should think about this as a covariant version of T naught naught. This P is the covariant version of pressure. So this E and P are scalars. This Q is the covariant version of the momentum density or the energy flux. And this script T is the covariant version of the stress, right? So this delta is the projector, spatial projector onto space directions, or space meaning orthogonal to U. And all the script letters, they are orthogonal to U, they are spatial quote unquote parts. Okay, so these two equations, they have nothing to do with hydrodynamics. These are just decompositions or identities. These are definitions of what you mean by E, P, Q, and T. And the main assumption of hydrodynamics is that both the energy momentum tensor and the current, of course, are written in terms of the useful variables, which in this case, temperature, velocity, and the chemical potential. So what I'm going to do, I'm going to write down my E, P, Q, T, N, and J as functions of this temperature, fluid velocity, and the chemical potential. Okay, so this is how I'm going to write down the constitutive relations. Okay, so the next slide is going to be a mess. So when I tell my students how to give talks, I always give this as an example of the type of slides that you're never supposed to show to your audience, because it has lots of little symbols and formulas, and people typically cannot listen. But I'm still going to do it. So so what I'm doing here is, remember, my constitutive relations are such that I have to write down this E, P, Q, T, J, and N as functions of my useful variables, which are temperature, velocity, and the chemical potential. So let's look at, say, E. So E, I'm going to write down as this big script E as a derivative expansion. So it's going to have a term that has no derivatives. So this epsilon as a function of T and mu of my zero derivative scalars, which are temperature and the chemical potential. And it's going to have terms that have one derivative. And it's going to have terms that are two derivatives, and so on. So E, this script big E, is a scalar. So I have to write down all possible one derivative scalars that are made out of my variables. And if I count how many scalars I can make out of my variables, it turns out there are only three. Okay, one is the derivative of temperature along the fluid velocity. One is the divergence of the fluid velocity, and one is basically the derivative of the chemical potential along the fluid velocity. There are only three one derivative scalars that you can write down. I'm sticking them here with arbitrary coefficients, epsilon 1, epsilon 2, epsilon 3, which are functions of my temperature, of my zero derivative objects, which are the temperature and the chemical potential. So I hope that's clear. Right? And then I do the same thing for all my other objects. This P, script P, is a scalar. It has a zero derivative part, which is a function of temperature and chemical potential. It has one derivative contribution. There are only three one derivative scalars, exactly the same one derivative scalars. I'm sticking them here with some coefficients pi1, pi2, pi3, and so on. And then I do exactly the same thing for the charge density, which is a scalar. It has a zero derivative contribution. It has three one derivative scalars with three coefficients. And then I do the same for vectors. Again, turns out there are only three transverse vectors. One is the acceleration, one is the gradient of temperature, one is the gradient of the chemical potential, and so on. The sigma mu is the shear tensor. It's some symmetrized trace subtracted derivative of the velocity.
Question?
Okay. Yep. Mm-hmm. Yes.
So why does, for example, this T appear in this combination T dot by T? And
just for dimensional reasons. It's just how I chose to define this epsilon 1. It doesn't have to appear in this combination. Yeah, it's just a convention. Yeah.
Okay.
Yeah. There is nothing important about it. Yeah. Yeah. Also, the fact that I put mu over T. Yeah, that's not important. I could have just written derivative of mu. Yeah.
And a question.
Yep.
Yeah. Why zeroth order terms are not dependent on velocities? I mean.
Yes, so this U is U squared is 1, right? So its principle depends on U squared, which is 1.
Oh, sorry. Yeah.
Right. So what you see from these things is that there are three, so to say, perfect fluid parameters. So these are the zero derivative things. So this is epsilon, P, and N. So these are the things that have no derivatives. These are exactly the things that will appear in a perfect fluid. And then there are 16 of all these other ugly things, epsilon1, epsilon2, pi's, thetas, nus. There are 16 one-derivative parameters, okay? So this is what you have to do if you just want to implement this idea that I said earlier, that simply write down everything with up to one derivative and see what happens. So what I want to do next, I want to talk about so-called frames. So frame is, in the word frame in hydrodynamics, it means simply a convention, how you choose to define temperature, velocity, and chemical potential beyond perfect fluids. So that's what I'm going to mean by the word frame in quotes. And to understand how this works, I think it's useful to look at this cartoon. So I'll give you a minute to read what is on the screen. Okay, so you see that when you talk about temperature, so it's maybe the simplest quantity that appears in these hydrodynamic equations, there is some subtleties in how you choose to measure temperature. So let me take these subtleties seriously. So when we teach statistical physics to our students, we say the temperature is something that is only unambiguously defined in equilibrium. And by definition, temperature is the quantity that is measured by thermometer. And so what I have here on the left, I have a representation of two identical equilibrium states. So this orange stuff is some equilibrium matter that sits in a box. And I have two thermometers that are supposed to measure the temperature of this matter. So what is a thermometer? Thermometer is a little heat reservoir that is coupled to a gauge, right? So I have a red heat reservoir that has come to equilibrium with my matter, and it is connected to a gauge, so the gauge measures temperature. And this is a green reservoir, part of my thermometer, that has come to equilibrium with my matter. It has connected to a gauge, and the gauge is showing some temperature. And this temperature will be the same if the states are identical and if the thermometers are properly calibrated. Now, but in identical non-equilibrium states, the same two thermometers will show different temperatures. Okay, so what I have here, I have identical non-equilibrium states. And now the same two thermometers, they will give me different readings. So why is this? So we know this very well, right? If we have two different thermometers that are constructed differently and they sit outside the window, if say the temperature changes very, very rapidly, maybe one of them will take longer to adjust to the changes in temperature than the other one. Also, if there is some some gradients appear, maybe the shape of this blob is different from the shape of this blob. And because of that, these two thermometers will react to these non-equilibrium states differently. So in general, the differences in these two thermometers will be small if the deviations from equilibrium are small, but they will be in principle different. So the measurements are given by these two thermometers. They can be interpreted as giving you temperature in two different quote-unquote frames. So some comments on frames. So frame is a definition of temperature, velocity, chemical potential beyond the zero derivative order. So frame is basically a convention. So a change of frame is a field redefinition of temperature, velocity, chemical potential by derivative corrections. And because we always work with some temperature, some fluid velocity, some chemical potential in hydro equations, we always use some frame. So it's impossible not to choose a frame. So you have to use something. And the energy momentum tensor and the current, they don't care which frame you choose to use. They're the same in all frames. But of course, in hydrodynamics, we only work up to a given order in the derivative expansion. So we have to truncate at a given order in the derivative expansion. This T and J will be the same in all frames up to a given order in the derivative expansion. And the moment we write down the constitutive relations with some specified values of those 16 parameters that I showed you earlier, you can view these constitutive relations as something that would specify for you a quote-unquote frame. So what this tells you is that there is no such thing as quote-unquote the Navier-Stokes equations until you specify your arbitrarily chosen convention. That is, for example, until you specify which thermometer you want to use. So for example, the choice of Landau is this. So Landau said, let us use field redefinitions and on-shell relations to push all the red terms here to order d squared. So you take all the terms that are crossed out, and you don't throw them away, but you perform one derivative field redefinition so that all these red terms, they now appear at this order d squared. Okay, and the only ones that you keep are this pi2, which you interpret as the bulk viscosity, this eta, which you interpret as the shear viscosity, and this gamma 3, which is going to be the charge conductivity or the electrical conductivity if you talk about the electric current. Okay, so the blue ones are the perfect fluid terms, the red ones are the Navier-Stokes terms. So the Eckart's convention is different. So Eckart said, let's take all the red terms that are crossed out and push them to order d squared, and you only keep the terms that are circled here in red, pi2, theta 1, theta 2. So Eckart says, let's keep those, the shear viscosity, and yeah, so all of those have been pushed to order d squared. Now, the fact that you can push most one derivative terms to order d squared by performing a field redefinition, so it's possible to do so, but the fact that you can do this does not mean that you have to. Okay, you can do this, but let's not do this. So let's now keep all possible one derivative terms for now. So for example, so let's keep all of those terms. So let's use the most general frame possible. Okay, in one derivative Navier-Stokes relativistic hydrodynamics. Does it matter? Does it matter which frame you use? So the choice of frame is not important from the point of view of the derivative expansion, for classifying transport coefficients, or for evaluating correlation functions. None of that matters. However, the choice of frame, or the choice of your convention, or the choice of your thermometer is going to be important from the point of view of the hydrodynamic equations themselves. So why is this? So this is because the hydrodynamic equations with their constitutive relations truncated at one derivative order, when you write them in different frames, you get different partial differential equations. Okay, so the mathematical structure of the equation will change depending which frame you're using. Okay, so the choice of frame may potentially affect such things as the well-posedness of the initial value problem for those partial differential equations, or lead to fictitious instabilities of the equilibrium state. So the main claim is this. So in the space of all of those 16 parameters that I said, so there is going to be a subspace where hydrodynamics is stable and causal. Some of those parameters that I said, you have to keep them non-zero positive and bounded from below. So there are some details in these papers, but the claim is this. So the frames of Landau, Lifshitz, and Eckart, they fall outside the stable and causal subspace. So there's some 16 parameters, there's some 16-dimensional space, and Landau, Lifshitz, or Eckart, they're outside of that good subspace. So what exactly are these coefficients that I have been talking about? I said there are all these 16 coefficients that appear in this one derivative relations. So at one derivative order, there are 16 parameters for fluids with non-zero charge density. And if you demand that the choice of your frame is consistent with extensivity in equilibrium, you can actually reduce this down to 14 parameters. Out of 14 parameters, 3 of those parameters are going to be genuine physical transport coefficients. So this will be the shear viscosity, the bulk viscosity, the measurable things, the electrical conductivity. These are the things that tell you about the actual real dissipation, that tell you how sound waves dissipate. So these are the 3 of those are going to be real, genuine, measurable things. So 14 minus 3, 11. So you're left with 11 one derivative quote unquote transport parameters. They're not physical transport coefficients. So this is something that you can eliminate by field redefinition or by using on-shell relations. So these 11 parameters, they have no fundamental microscopic definitions. They have no Kuba formulas. If you go into order d squared, you're not going to fix them, because if you go to order d squared, you're going to introduce even more things at order d squared. So these extra one derivative parameters, you should be thinking about them as a UV regulator, which makes the UV of hydro consistent with relativity. Okay, so these parameters ensure that the gapped modes are in the lower complex half plane, just like in the Israel-Stewart theory. And I said there are 11 of them, but most of them you can actually just set them to 0 without sacrificing stability and causality. So it's only very few of them that are actually important. So in kinetic theory, these arbitrary parameters that appear as integration constants that parameterize the 0 modes of the collision operator. So if you think about the Israel-Stewart theory as a Pauli-Villars regularization, think about these stable and causal frames as a high derivative regularization, except the regulator, it formally appears at the same order as viscosity. So it formally sits at one derivative order, but if you want to perform a field redefinition, you can push it to order d squared.
I have a question. Yep. Can I ask?
Yes.
So there is this there is a derivation of hydrodynamic equations using the ADS-CFT correspondence, which uses the Einstein equations.
Yes.
And it's a very well-known development. How does that square with this? I mean, doesn't that give you some unique equations? Because Einstein equation is unique.
No. You still have to make a choice. There are still some integration constants that you can choose to set them to 0. And so there is a choice. Like if you read, the first papers on the fluid and gravity correspondence, then you will see that the authors have made certain choices, and the certain choices amount to the convention of Landau-Lifshitz.
I see.
There's also the same arbitrariness that exists in that construction. Yes.
Okay, thank you.
Now, again, so for the purpose of doing the derivative expansion or for classifying the transport coefficients, this choice is not going to be important. But if you actually want to, to solve for the nonlinear evolution of the fluid, like imagine that you literally want to write a computer program that, you give some initial state of the fluid and you want it to undergo as a function of time nonlinear evolution, then you will not be able to do it with the Landau's convention.
I see. Okay.
So a simple example would be, say, talking about conformal fluids. So what I was talking about before did not require conformal symmetry, but if you happen to be interested in conformal fluids, then in conformal field theories, there are some simplifications that, tell you about simplified thermodynamics and hydrodynamics. There are some constraints on the equation of state. There are constraints on one derivative transport parameters. So speed of sound squared is 1/3, the bulk viscosity is 0. And, the simplest useful frame that you can choose, you can set all of those transport parameters to 0, except for, say, pi1, θ1, and nu3. So there are only 3 that you need for charged fluids. And for stable and causal conformal hydrodynamics, if you just take your pi1, θ1, and nu3 to satisfy these inequalities, you're guaranteed to have well-behaved, stable, causal, relativistic hydrodynamics that can be coupled to Einstein's equations, does admit a well-defined initial value problem, and does not require any extra variables besides the standard variables that you use in thermal physics, temperature, velocity, chemical potential.
Sorry, hello. Can you just remind me again, what were these pi1, θ1, and nu3? Which coefficients are these?
Right. So pi1 is basically, so see, the important ones are the ones that are going to come with time derivatives, because these are the ones that are going to change the structure of your equation to make it hyperbolic. Okay. So normally these time derivatives are eliminated by using either a field redefinition or some kind of on-shell relation from perfect fluids. But I'm saying let's keep them, right? So the pi1 is the one that comes with a time derivative here, so it will be related to this epsilon1 here. So θ1 is the one that comes with time derivative of the velocity in the energy flux, and gamma1 or nu1, sorry, is the one that comes with the time derivative of temperature in the charge density. So this is basically, so you can think about them as some kind of relaxation times. So I haven't talked about this, but you can give them physical interpretation. You can give these parameters a physical interpretation as quote unquote relaxation times that relax your fluid velocity and temperature to fluid velocity and temperature in the Landau's definition.
Yeah, okay. So, I mean, it's not evident to me, but if you just turn on this, it's not clear to me that the constitutive relations you get are Weyl invariant. They're the invariant under Weyl transformations and so on. Are they? Are they invariant under Weyl transformations?
Under Weyl transformations? Yes. Yes.
Okay.
Yes. So the Weyl transformations, they will relate different terms in this constitutive relations. So they will relate like epsilon1 pi1, they will relate pi1 pi2, they will relate theta1 theta2, they will relate gamma1 gamma2. And so for example, if I'm keeping pi1 non-zero, then in order to be consistent with conformal symmetry, I will also have to keep epsilon1 to also non-zero.
Okay. Okay. Thanks.
G is electric current.
It is a current of a global U1 symmetry. So I take my U1 symmetry to be a global symmetry, not a gauge symmetry. So this is something like the baryon number current. Yeah, so the electromagnetic field here, if I talk about electromagnetic field, it's not dynamical. So in this case, there is no dynamical electromagnetic fields. So it's literally the best way to think about J, I think, is like the baryon number current corresponding to a global U1. So sigma will be, say, the baryon number conductivity. Okay, so the bottom line for my first story, and this was just the first story, is that so choose a physically sensible thermometer or velocimeter, and then the Navier-Stokes equations, they can be happily unified with relativity, and there is no need for extra UV degrees of freedom. So the next step that I'm interested in is to develop numerical codes and apply them to physical systems. But there's also a question. I think based on what I said, there's a very natural question to ask. So the question is this: sensible relativistic hydrodynamics, it seems to require that its equations contain non-hydrodynamic parameters, which have the interpretation of a UV cutoff. So if your equations have these parameters that are strictly speaking parameterized physics outside of the validity regime of your theory, when you solve the equations, the solutions will also depend on those non-hydrodynamic parameters. So the solutions will also depend on the parameters that are outside of the validity regime of the theory. So you can ask, does hydrodynamics actually have predictive power for nonlinear evolution? In other words, can you actually ensure that when you set up, partial differential equations of well-posed relativistic hydrodynamics, you're always going to guaranteed to find solutions that are not contaminated by the high energy UV physics? Okay, and it's not clear to me that this is the case. It's not just a problem with this formulation of hydrodynamics that I described. It's a problem with any formulation of relativistic hydrodynamics. So Israel Stewart, that people have been using for decades, say to study the quark-gluon plasma, has exactly this problem. And I'm not aware of any good systematic treatment to say that it is possible to ensure that the low energy physics can be separated from the high energy physics. And we know that in general it cannot. You look at a waves, in the sea, and you have some very long wavelengths wave that comes to the shore and breaks. And when it breaks, it becomes a very short wavelength. So this is the result. As the result, as a result of time evolution, long wavelengths fluctuations become short wavelengths fluctuations. So in principle, your effective theory breaks down just by waiting. But I don't know if there's any notion of RG, for example, for hydrodynamics that can ensure that indeed you can have a separation of scales. if you have thoughts about this, I would be interested to talk about this. So this was my first story. I think I'm sort of running behind in my time. So can I talk maybe 10-15 minutes?
Yeah, 15 minutes.
Yeah. Okay. So yeah. Okay. So I'll try to summarize the second story qualitatively. So things beyond classical hydrodynamics. So I want to ask this question. Okay. So this is a reminder of classical hydrodynamics, some conservation equations. You introduce some proxy variables. This beta will be combination of temperature and the fluid velocity. You have the constitutive relations. Alpha is like the chemical potential, is a proxy for chemical potential. So what I want to do now, I want to couple my theory to external sources. So couple it external metric, external gauge field. Okay, so I want to see how the near equilibrium physical system reacts to infinitesimal external sources. Again, I want to look at very, very simple linearized setup. I want to make my life as simple as possible. So I couple my energy momentum tensor and the current to external metric and external gauge field. Okay, and so now my hydrodynamic equations will depend on the external metric and the external gauge field. So I can solve these equations, and when I solve these equations, I will find my temperature and the fluid velocity as a function of the metric and the gauge field. I will also find the chemical potential as a function of the metric and the gauge field. I can stick them back into the constitutive relations, and now I will find how my energy momentum tensor and the current depend on the external metric, how they depend on the external gauge field. Right? So this will be the prediction of hydrodynamics, how my macroscopic system responds to long wavelengths external perturbations of the metric and the gauge field. Now, if you take these equations, you expand them to linear order in these external sources. Okay, so energy momentum tensor, something that the piece that sits in flat space, no external gauge field, some constant piece, plus there is going to be some linearized response proportional to delta G and delta A. Is there a question? Question? Yes? No? No? Okay. Right. So and the same for the current. So there is going to be some prefactors that sit out in front that parameterize the response, the linearized response of my energy momentum tensor and the current to the external metric and the external gauge field. And so these coefficients, there will be predictions of classical hydrodynamics. Okay. So the linear response theory tells you that these coefficients that multiply the response to the metric and the gauge fields can be given a physical interpretation of retarded functions of the energy momentum tensor and the current. So classical hydrodynamics, it gives you predictions for those retarded functions of conserved densities and fluxes in equilibrium. For example, if you look at the retarded function of charge density with charge density, it has this form. D is the diffusion constant of this sort that I talked at the beginning of the presentation. Chi is the charge susceptibility, d and d mu. It basically tells you about the mean square fluctuation of your charge, of the baryon number or particle number in equilibrium. And so this is the retarded function of the xy component of the stress. So this is txy in equilibrium. So P is the pressure. This comes from perfect fluids. Omega is 1 power of frequency times the viscosity. This comes from Navier-Stokes. Then there's going to be 2 derivative terms, which I'm not writing there. Okay, so these are predictions of classical hydrodynamic equations. Okay, so they do not depend on which version of hydrodynamics you're using. Are they universal predictions for observables? You can use these relations to write down so-called Kubo formulas for viscosity, diffusion constant, whatnot.
Sorry, what are functions alpha and beta in the fluxes? Alpha and beta, what is it?
Yeah, these are just proxies for temperature and fluid velocity. So think about them like this, right? So temperature, think of temperature as 1 over square root of beta squared. and think of fluid velocity as this, right? So this is just shorthand notation so that I don't write u comma t. I just write beta. This is just temperature and fluid velocity. Right. So these don't depend on which variables you use, right? So these are predictions of hydrodynamics that are independent on which variables you use, which frame you use, whether you use Israel-Stewart or this causal Navier-Stokes. This doesn't matter. So these are exactly the same. Okay. So question that I want to ask is this: are these predictions of classical hydrodynamics actually correct? Okay. So after all, classical hydro, meaning hydrodynamics as partial differential equation, is just a toy model of fluids, and nature may or may not care for our toy models. So let's look at limitations of hydrodynamics. Okay, so we know that macroscopic stuff is made out of microscopic stuff. And if you think about analogy with quantum mechanics, in a quantum vacuum, virtual particles are constantly produced and absorbed due to quantum fluctuations. So similarly, in a macro state, virtual sound waves are constantly produced and absorbed due to statistical fluctuations. Okay, so here I have a cartoon of, say, temperature as a function of distance, and this thick blue line is a solution of my classical hydrodynamic equation. But there can be fluctuations. So I have some statistical fluctuation that happens here. The statistical fluctuation generates sound waves that propagate in my fluid. And these sound waves that are statistically generated, they will back react on my thick blue line. And so they will change the solution. Is this important? Well, so the claim that has been known for a very, very long time is that even if you're interested in macroscopic, long-time, long-distance response near static equilibrium, classical hydrodynamic equations which ignore the back reactions can lead to predictions which are qualitatively wrong. And I do mean qualitatively, not quantitatively. This has been noticed, to my knowledge, for the first time in the early days of molecular dynamics simulation. Basically, computers started to become more and more used in physics, and people said, let's take a gas of billiard balls or rigid disks, and let's time evolve them, and let's see if the evolution or the correlations actually follow Navier-Stokes. And it turns out there are some deviations from Navier-Stokes that are pronounced for long wavelengths physics, not short wavelengths physics. So the rest of my talks will be comments on this claim. So as a simple example, let's look at the viscosity. So what is viscosity? Viscosity is something that tells you about the momentum transfer between different layers of fluid. So what I have here on the left is a picture of my fluid denoted by yellow arrows. The fluid moves from right to left. The fluid moves fast here on the bottom. The fluid moves slow here on top. The thin blue lines are the particles. So my fluid, let's pretend my fluid is made out of particles, and these particles, they jump between, from place to place, and they can transfer momentum. So for example, this particle can go from a fast layer on the bottom, it can jump to this slow layer on top, and as a result, it can transfer momentum from the bottom layer to the top layer. So this process is precisely what viscosity parameterizes. So the way you describe this quantitatively is you relate stress, in this case, the Txy component of stress, to the partial y Vx, so the derivative of the fluid velocity. And there is some coefficient out in front, which is the viscosity. This viscosity can also be related to correlations of stress. For example, Txy, retarded two-point function of stress at zero spatial momentum. The viscosity appears here like this. So omega is the frequency, P is the equilibrium pressure. So in a gas, again, it's well known since I think the time of Maxwell and Boltzmann that viscosity is proportional to the mean free path. So rho is the density, the mass density, or the energy density. V is the mean thermal velocity of your molecules. Now, okay, so this is just something that's well known, but think about this. So momentum can also be transferred by collective excitations. Okay, so I have the same picture. but now I have my sound waves that have been statistically generated in the fluid. So in a gas of sound waves, how far does the sound wave propagate? So how far it propagates, it will be inversely proportional to the viscosity. It will be also inversely proportional to momentum squared, right? So this is the standard damping of sound waves proportional to the viscosity and you know, the wavelengths. So if you think about the contribution of, so E is energy density, P is pressure, right? In a non-relativistic fluid, this would be mass density in the denominator. All right. If you now want to think about the contribution of the sound waves to pressure, to viscosity, you have to sum over all possible, you know, types of sound waves that get excited. So you sum over all possible K, over all possible momenta here. So you do this integral in d spatial dimensions. You integrate d dk, and you know this result has to be proportional to the mean free path. So basically sum over all this mean free path. So T is just for dimensional units I have put in here. But the important thing is 1 over the viscosity in the denominator and 1 over K squared. So what happens if you do this integral in 3 space dimensions? If you do this integral in 3 space dimensions, you get something that is inversely proportional to viscosity over entropy. It will be UV divergent. There is some UV cutoff. And so that's it. But if you think about 2 space dimensions, this integral will be infrared divergent in 2 dimensions. And this tells you that, you know, this back reaction you cannot ignore in 2 space dimensions. So what you're looking at here is that this is the physics of thermal fluctuations. So it is invisible if hydrodynamics is viewed just a collection of partial differential equations. So another comment is that, because you see, the contribution to viscosity here is inversely proportional to what you thought was your viscosity. So if your viscosity is very, very small, the correction to viscosity will be very, very large. So you will be doing a calculation that is not reliable. So if you think h over s can be arbitrarily small, think again. So maybe it cannot be very small. And the third comment from the previous slide is that classical hydrodynamics may actually be irrelevant to physics in 2+1 dimensions. So how do you describe these effects quantitatively? The simplest way to describe these effects that people have been using for quite some time is to add random fluctuations through the means of random currents and stresses. People call them noises. So when you write down the energy momentum tensor, you know, say that it is made out of 2 parts. One is the classical part and one is the random part. So this T mu is some stochastic variable, and the same for the current, this little j, some stochastic variable. So when you look at correlations in the fluid, you average over these noises, tau and j, with some weight. Okay, you have to perform the path integral over these noises with some weight. And the weight, this action, is quadratic in the noise for long wavelengths fluctuations. This is essentially by the central limit theorem, because you average over a large number of independent volumes whose size is about the correlation length in a fluid. And so the number of such volumes is basically, it's basically the wavelengths over the correlation length cube. And so this tells you this is quadratic in the noise, and the width of this action will be determined by demanding that the equilibrium 2-point function satisfy the fluctuation dissipation theorem, which is the relationship between the symmetrized 2-point function and the imaginary part of the retarded 2-point function. Okay, so you do this. You can compute, so I'll probably skip the details here. So you can compute the 1 loop correction to the viscosity, and so this is what you're going to find. So this is a result of the 1 loop calculation to the stress, to the retarded 2-point correlation of stress in 3 space dimensions. So the red terms are the ones that come from classical hydrodynamics. The purple terms are the ones that come from the 1 loop correction. So this is some cutoff dependent correction to pressure. It's like cosmological constant, so that's not very interesting. There's a correction to viscosity, which is inversely proportional to the viscosity itself, cutoff dependent. Okay, this is more interesting because this can potentially be large if your viscosity is small. And then this one, it's actually cutoff independent. So this is a universal infrared physics that does not depend on the cutoff. So what you can see is that fluctuations are mandatory for small viscosity physics. And moreover, you look at this, this has omega to the 3/2. Okay, it's a fractional power. It's a non-integer power. Second order hydrodynamics comes at omega squared. So this tells you that fluctuations are more important than second order hydrodynamics. So even for the simplest linearized perturbations near thermal equilibrium, second order hydrodynamics gives you prediction that is less important, and it's actually incorrect because you have to include this omega to the 3/2. So in real time, this omega to the 3/2 gives you a power law decay of correlations, and this is actually more important than first order hydro. This is what people call the long time tails. This is a power law decay of correlations, not exponential decay. So in two spatial dimensions, this omega to the 3/2 becomes logarithmic, becomes log omega. So if you now think about the Kubo formula for viscosity, that does not exist. So viscosity actually diverges as you take the limit of zero frequency. Now, if you're thinking about doing this in classical holography, then in classical ADS-CFT, so the quantum field theories that one describes using classical Einstein's gravity or even corrections to Einstein's gravity are large N field theories. And large N limit does not commute with the hydrodynamic limit. So in a large N field theory, this non-analyticity will be 1/n suppressed compared to this leading term. So this fractional power is not visible in classical holography, because in classical holography, you take the n to infinity first, and then you take the limit of small frequency. Okay. Now, of course, in the real world, frequency is not exactly zero, n is not strictly infinity. So which one is more important? Okay, so you have to calculate. So there is an analogy with quantum gravity, which I think many people are familiar with. And the analogy with quantum gravity is this. So as I said, the one loop corrections due to statistical fluctuations of sound waves, they will be more important than high derivative corrections to hydrodynamics. And in perturbatively quantized quantum gravity around flat space, you can ask a question about, say, the two-body interaction potential. And they will have contributions, this will have contributions from Einstein's gravity, and it will have contributions from high derivative corrections to Einstein's gravity. But you can also ask a question about, what about the quantum effects? What about the graviton loop that can propagate between the two sources? And if you look at this one loop diagram, you realize that the graviton loop actually gives you a power law that is more important than this exponential piece that comes from the high derivative gravity. So this is, again, an example when the quantum effect that comes from the Einstein's gravity is more important than the high derivative effect that comes from classical gravity. And so this is very analogous to what happens here.
Sorry, Pavel, I know that you're running out of time, but if I may just, ask something. So in both these examples, what is important depends on what you're talking about, right? It depends on the physical problem. I mean, in some sense, there are different parameters which suppress the different terms. And
yes. It depends on the question. It depends, of course, on the question that you want to ask. Of course, what I did here, I judiciously chose question whether the effects I'm interested in are important. And morally speaking, this is what happens here is that when you have massless degrees of freedom, so here the massless degrees of freedom is the graviton, and here the massless degrees of freedom is the sound wave. So what happens is, whenever you have a theory with massless degrees of freedom, when they run massless degrees of freedom run in loops, they can potentially give rise to interesting infrared effects. Okay, and so this is just
for example, like in this, in the larger thing commuting, it is true that like long time tails correct the long time predictions, but but the times you have to wait for are kind of, like long, right? There is some power of n or something.
Yes, of course.
For them to be appreciated.
Yes, of course. And yeah, so if we think about applying this to, QCD, which has n is equal to 3, but also omega is not strictly speaking 0, because to get 0 omega, you need to wait infinite time. You're never going to get this. And moreover, all experiments are performed in finite volume, so momentum is also not strictly speaking 0. So, the real system, you probably will be looking at slightly non-zero omega, slightly non-zero k, and non-infinite n. And you basically, in these equations, you have to really plug in the numbers to see which ones can be more or less important.
Right. Yeah. Thanks.
Right. So the bottom line for what I said so far is that using classical hydrodynamics to evaluate this response to sources is unreliable. So the short time statistical fluctuations give rise to infrared late time correlations. So the deviations from classical hydro are more pronounced at small viscosity, and stochastic hydro predicts that these correlations are universal, and they're determined only by thermodynamics and transport coefficients, viscosity, conductivity, and so on. Now, the problems of classical hydro don't end here, especially if you want to do high derivative hydro. Now, I know I don't have time for this, so I probably will skip all of these things that I was going to talk about. I was going to talk about the Schwinger-Keldysh effective theory, the effects that you can see in the Schwinger-Keldysh EFT. So what I will talk about is probably this.
Okay. Perhaps, Pavel, like if you can just summarize,
Right.
Completely skip it.
Right. So okay. So let me summarize. Okay. So what I want to do is so I'll try to finish within 5 minutes. Okay. So I want to go beyond this naive stochastic hydrodynamics. So I said the noise is only Gaussian when momentum is going to 0 or infinite wavelengths. So what if you want the derivative expansion, meaning you go beyond the strict k goes to 0 limit? This will also tell you that you have to take into account the non-Gaussianities of the noise. Now, the width of the Gaussian, meaning the width of this Gaussian in this stochastic approach to hydrodynamics, so the width of this Gaussian was fixed by the fluctuation dissipation theorem for 2-point functions. But fluctuation dissipation theorems, they also exist for all n-point functions. So the 2-point function fluctuation dissipation theorem is just a simple example. So you can ask, how do you make sure that you also respect all of those fluctuation dissipation theorems for all of those n-point functions? So it's a question. So another question is, that classical hydrodynamics, when you take the variation of these classical objects with respect to the source, you are going to get a unique answer. So what is this answer? This answer turns out to be the retarded response function. So if you look at response functions that are not retarded, these functions are invisible to classical hydrodynamics. Okay, so they're symmetrized. They're invisible to classical hydrodynamics. But higher point non-retarded functions, they cannot be related to retarded functions through the fluctuation dissipation theorem. Okay, it's only for the 2-point function, I think also for 3-point function, that all the functions can be related to the retarded ones through the fluctuation dissipation theorem. So if you look at, say, 4-point functions, then there are non-retarded 4-point functions that contain low energy information. But that low energy information is completely inaccessible to hydrodynamics, because hydrodynamics only knows about the retarded ones. So how do you access that extra low energy information, and does this low energy information change the correlation functions or change the response to your sources? And it turns out that it does. And in order to answer all of those effects systematically, what you have to do, you have to use the Schwinger-Keldysh effective theory that people have started working on quite intensely in the last few years. So the early works on that, I think it goes back to the MSR field theory in the early 1970s. But starting, 2015, several groups, especially Leung, Gloriosa, and Crossley, and also Hell, Loga, and Rangamani, they have really been pushing this program. So this is not my work. So if you want to know more about these theories, ask Loga or Mukund or Felix or Hong or Paulo. There has been a lot of work figuring out the machinery behind how to describe all of those effects systematically using effective field theory. So my interest here is that to take that mathematical machinery and see what one can actually do with it in practice in terms of actually evaluating measurable correlations. Okay, and it turns out that some of these effects that I talked about here, say the effect of higher point non-retarded functions, they can be evaluated quite straightforwardly using this mathematical machinery of the Schwinger-Keldysh effective theory. So there's some details that I'm going to skip here, but the summary is going to be this. So the Schwinger-Keldysh effective theories, they can be thought about using the two types of fields. One type of field is you can call a classical field. So this is the field that you are used to. This is like the temperature in the fluid mechanical, or the fluid velocity in the fluid mechanical equations. But there is another type of field, which is you call the A-type field. So this is the field that tells you about the noise or statistical fluctuations. Okay. And the way you organize the effective action in those Schwinger-Keldysh field theories, you organize them as power expansion in powers of those stochastic fields. So you have terms that are linear in these A-type fields, quadratic, and then cubic, quartic, and so on. So if you look at the fields, the terms that are linear in the A-type fields. So this is the terms that give you the classical hydrodynamics. So this capital F will contain all the classical equations of hydrodynamics with all the nonlinearities, all of the constitutive relations that I talked about in the first part of the talk, they will be contained in this F. This G here in the second line, these are the terms that are quadratic in the A-type field, and these terms that are fixed by the fluctuation dissipation theorem in terms of the classical transport coefficients. So these are like the quadratic Gaussian noise whose strength is fixed by the fluctuation dissipation theorem. And the terms here will depend on the viscosity, conductivity, and so on. But the thing that I want to emphasize is that there are also Gaussian terms that are not fixed by the fluctuation dissipation theorem, that are sensitive to the non-retarded function. So these terms in the third line, they're not fixed by FDT, and they're invisible to classical hydrodynamics. So the difference is the second line is determined by the viscosity, conductivity, and so on. But the third line needs genuinely new information because it's the genuinely new information that sits in the non-retarded functions. So you can call things that sit in the third line, quote unquote, stochastic transport coefficients. They're not normal transport coefficients. And the fourth line are completely invisible to classical hydrodynamics. There are even more stochastic transport coefficients that sit here. So you can think about these terms as quote unquote new interactions or new types of interactions that are invisible to classical hydro. And the important thing is these new interactions are invisible to classical hydro at tree level, but they can contribute through loops. And through loops, they can contribute to infrared low frequency, low momentum effects. Okay, so what you have here is that this is something that your classical constitutive relations completely do not see. But at the loop level, these things contribute to infrared correlations. So they contribute to infrared response to infinitesimal, external metric, infinitesimal external gauge field. So this is the main point, is that just looking at normal transport coefficients, like the viscosity, is not enough to characterize the infrared response of the fluid. Okay, so this is my conclusion. Okay, stochastic coefficients, so they're invisible in classical hydro, but they do contribute through loops. They give rise to infrared effects that are derivative suppressed in 3+1 dimensions compared to viscosity. And so these effects are different from those long time tails that I was talking about earlier. Now, Kubo formulas for those stochastic coefficients, they involve the non-retarded functions. So this is different from, the viscosity, the conductivity. If you want to connect, if you want to do so-called UV matching, if you want to connect the viscosity to microscopics, you use retarded functions. If you want to connect the stochastic coefficients to the UV theory, you use non-retarded functions. So the point is that knowing the macroscopic classical effective theory, even to all orders in the derivative expansion, is not enough to correctly describe macroscopic infrared correlations because of those loop effects due to stochastic transport coefficients. So I want to end with an encouragement for students. As a student, one often tends to think that all interesting questions in physics have been answered many years ago by the great. So hydrodynamics is an ancient field by modern standards, and people are still trying to figure out some very basic questions, as hopefully I emphasized in this talk. And if, as a student, you work in a field that is less than 200 years old, do not lose hope. There are surely many fundamental things left to discover. So that's all. Thanks for listening. Sorry to go over time.
Oh, thanks, Pavel, for the very nice talk. So it was really, really pedagogical. So thanks. Maybe we can unmute the microphone and clap up.
Yeah, thanks.
Thank you very much.
So it's the time for questions. So if you have any question, please unmute your microphone and carry on.
See you guys.
No.
Yeah, there is a
quick question about the first part of your talk. I just wanted to ask you something. So, so you have explained that there's this requirement of going into some new kind of a frame definition, right?
Yep.
So usually when people talk about Landau and Eckart frames, there's this idea that this velocity that you're defining, that has a physical interpretation of telling me, which direction energy is flowing, or let's say which direction charge is flowing, right?
Right.
So now if you go to a different frame, would you be, it's of course going to be some field which you're solving for, but would that have a natural physical interpretation like that? Or
I don't think it will have a nice physical interpretation. I don't think so. So one way you can see it is that the terms that are important to make relativistic hydrodynamics stable and causal are terms that involve these time derivatives. So all this notion about, so say if you want to connect the fluid velocity in this frame that gives rise to well-defined equations to the fluid velocity in the Landau frame, that relation has to involve time derivatives. And this kind of has to be like this because, the equations end up being hyperbolic. And for hyperbolic equations, you also need to specify the initial velocity, the initial time derivative of your function, in addition to the initial value of your function. So the best, perhaps the best physical interpretation I can give is that those coefficients that come with time derivatives here, I think about them as quote unquote relaxation times that would tell you how the temperature in the fluid velocity in this frame, how they would relax to the temperature in the fluid velocity in the Landau frame.
I see.
So this is like one, mathematical interpretation. A physical interpretation is, I think physical interpretation is consistent with this picture of different thermometers, different velocimeters, even though, to be honest, I have not thought about how exactly to design an actual thermometer that would measure for me a temperature, in, a particular frame, given particular values of those coefficients. So, and another comment that maybe I want to make about this is that if you think about the Landau frame that is used, for example, in the context of the Israel-Stewart theory, then what people do, people say, okay, let me take my energy momentum tensor and find its time-like eigenvector This will be the fluid velocity, and the eigenvalue will be related to, energy density or temperature. But all of that only requires that you know the energy momentum tensor at a single instant of time. At a single instant of time, and you're able to reconstruct the velocity and temperature in the Landau frame. Now, from hydrodynamic point of view, I don't know if this is very natural, because if you only know the state of your system at a single instant of time, you don't necessarily know if your system behaves hydrodynamically or not, right? Because if you only have given a snapshot of your system at t is equal to t naught, you don't know if you're taking a snapshot of a hydrodynamic evolution, or you're looking at a snapshot of some completely weird time evolution with huge time derivatives. And so the fact that you are able to reconstruct in the Landau's approach the temperature and the fluid velocity only by looking at an instantaneous value of the energy momentum tensor, to me, I find it sort of unsatisfactory, because you don't necessarily know if you're looking at a hydrodynamic state. Yeah.
I see. Thank you.
So there are two raised hands. So first, Sampan Vadodi, please go ahead.
Yeah, my question is from the first part as well. So can you eliminate all the 11 parameters for any general frame?
Can I eliminate all of those?
Yeah.
Well, I can eliminate no more. So I have to leave the 3 parameters. So for example, the shear viscosity, I cannot eliminate. The bulk viscosity, I cannot eliminate. The charge conductivity, I cannot eliminate. Everything else, I can.
Okay, for any general frame, right?
Yes. So,
okay, so
like,
that would mean that for any general frame, the energy momentum, the tense stress of energy momentum will always be 0 for any conformal theory.
No. I mean, the bulk viscosity will be in general non-zero.
For conformal theory.
Second?
For conformal theory.
Yes, for conformal theories, the stress of the energy momentum tensor will be 0. So this is regardless of the frame, and this is like in the example here. So these relations, they ensure that the trace is 0, but there is also, of course, there are stronger constraints due to the Weil rescaling, and not just that the trace is 0. But this will guarantee for you that the trace is 0, right? So in a conformal theory, bulk viscosity is just 0, so there is no need to eliminate it because it is just 0, and everything else is just a consequence of a conformal theory. So you can have these coefficients to be non-zero as long as they satisfy the equations that are written here on this slide. So as long as these equations are true, the trace will be 0, and your energy momentum tensor will be consistent with being a CFT energy momentum tensor.
Okay, so
but you can have those things non-zero.
They don't necessarily need to be 0, but they have to follow the relations.
No, they don't have to be 0. Yes, but they have to obey those things. That's right. Yeah.
Yes.
Okay, so next raised hand is by Logo. So Logo, please go ahead.
So Pavel, this is about the last thing that you're talking about regarding these extra coefficients.
Yep.
So are there any particular microscopic examples where these extra coefficients have been calculated, like say in kinetic theory or something? Do you know?
Oh, not to my knowledge.
Okay.
Actually, not to my knowledge. Kinetic theory.
But do you think they? Let's say. Yeah, please go ahead.
Yeah. So if I think even I mean, so okay. So the presence of these types of terms, okay, in general effective field theory, it can be argued on general grounds, right? It's just write down everything that is consistent with KMS and other symmetries. You just write down these terms, right? So what we wanted to do in this paper with Akash is to see what would be the implications of those terms. Even for those terms, we had some partial Kubo formulas for those terms, but we didn't have like a complete relation that says, this stochastic transport coefficient in relativistic hydro is given by that particular correlation, non-retarded correlation function. We had some partial connection to that, but not full. So even I would say the full Kubo formulas that would tell you exactly what correlation function you have to calculate of what operators with what indices, that is something that still has to be worked out in general. In kinetic theory, I don't even know how to approach those calculations in kinetic theory. I mean, I have not thought about it, but like kinetic theory might not even be sensitive to those things. But I'm not sure about this 100%.
So you're saying you're saying you might have to go beyond the Boltzmann equation or something to calculate them? I'm trying to understand that. That is a possibility.
Yes, correct. Yes, that's my statement, yes.
Okay, thanks.
Yeah, but there is definitely some quantum field theoretic relation that says, stochastic coefficient, θ1 is equal to blah, this particular non-retarded 4-point function of, certain components of, currents, energy momentum tensors. And that has not been worked out in full detail.
But you think it is computable? Let's say in 5-4 theory,
I think so. I think so. Yes, it's it's a well-defined quantum field theoretic observable.
Okay. I mean, I agree that it's very defined, but I was wondering whether you think it's computable by the present technology. I mean, this is a very big question. You don't have to answer it, but yeah.
Well,
can you get a feel of what you think?
Honestly, I do not know. that's and I have not thought about this carefully. That's my honest answer. My gut feeling is yes, but the honest answer is I haven't thought about this deep enough. Yeah.
Okay, thanks.
Yeah.
Okay, Akhil has a question. So Akhil, please go ahead.
Hi, I was there are these relation bounds on this extra coefficients in the constitutive relations which we need for well-defined hydrodynamic equations, right? I was wondering, could they necessarily mean some fundamental constraint on measurement apparatus or temperature gauge or something? As in, could you physically interpret it as a inherent property of your measurement apparatus or something?
I think it should be possible to do so. Now, one way to think about those coefficients, say this coefficient here, epsilon 1. So if you think about, say, the Landau frame, so Landau frame sets all of those epsilons to 0. So the Landau frame says the following. If you take, and this script E in the left-hand side is morally speaking T naught naught, okay? So the Landau is the energy density. So the Landau frame says the following. If you take the energy density, it is related to temperature by this. Energy density is equal to epsilon of T. It's some function given by this equation of state. And so what this tells you is that the moment energy density changes in your fluid, the temperature adjusts itself instantaneously. It's just like this. Just because this energy density is just some algebraic function of temperature, right? So the moment energy density changes, the temperature changes instantaneously because temperature is just an algebraic slave to temperature. So this is the Landau's prescription. So there is no delay, so to say. So your thermometer that measures temperature has an instantaneous reaction. And this, I think, can be related to violation of causality. Here, I mean, it's not maybe immediately obvious that if you have a thermometer that has an instantaneous reaction, that this violates causality, but it seems to be one of the requirements that this coefficient has to be non-zero in order to maintain causality. So in some sense, yes. So the values of these coefficients can be related to, say, delayed response of the thermometer, if you think about it this way. So that, yeah, and then but then these equations here, these are just quantitative inequalities. So right, so they tell you the delayed response has to be bounded from below by that, and I think okay, so now I'm speculating. Okay, so I will be speculating that any physical thermometer that can measure temperature in a fluid, that they will have to have their response to changes in energy density that is bounded by those inequalities. But that's again, I think it's a reasonable sounding speculation. So yeah, so that's I guess what I can say about this.
Any other questions? Okay, I think there are no more questions. So thank you very much, Pavel, once more. So
yeah. Thanks everyone.
Thanks everyone for joining. So I wish everyone to have a very nice time. Okay. So
yeah, thanks. See you.